Well, guys, we'll go ahead and get started. So, last class we started a very important topic, topic of resonance, and we talked about frequencies of vibration, and that all objects, every object has a natural frequency of vibration. And what we mean by that is, if you hit it and you cause it to oscillate, or if you pluck a string, or if you have a swing and you let it swing on its own, you don't apply any force to it, you just let it kind of move on its own, it'll vibrate or it'll move at a certain frequency. And so mechanical objects have a natural frequency of oscillation. We call that the resonant frequency. But so do circuits. And so I showed you how you can actually put energy into a capacitor, and then if I have an ideal capacitor, it'll hold that energy forever. But what I did was I hooked it to a switch and an inductor, and we made a circuit to where when the switch is closed, the capacitor will discharge through the inductor and build the magnetic field up around the inductor. And as long as the current is flowing from the capacitor to the inductor, that magnetic field is sustained. But when the capacitor discharges, there's no more current to maintain the magnetic field around the inductor, and then it starts to collapse. While it's collapsing, you have Faraday's law. You have a magnetic field, you have a conductor, that will be the inductor, the coil, and the field is collapsing, and so you have everything you need to induce a voltage, and since you have a closed circuit, a current will flow, and that current will flow into the capacitor and charge the capacitor back up. As long as I have ideal capacitors and inductors, I never get any power loss. So the energy just kind of goes back and forth between the capacitor and the inductor, and it does that at a certain frequency. So that's one thing we learned. Something else we learned is the frequency at which objects resonate or vibrate. I shouldn't say objects, I should say circuits. That you can think of that charging and discharging of the capacitor, the discharging of the capacitor and the charging of the inductor and vice versa, that goes back and forth. Any kind of back and forth movement, you can give a frequency number to it. So many hertz, or so many swings per second, or cycles per second. And what we learned about those electrical oscillations, when we talk about electrical resonance, is that happens when this is true. So for a particular circuit, the resonant frequency is defined to be the frequency at which the two reactive components, the inductor and the capacitor, they have an equal ohmic value. But since on our impedance diagram we know there's R, there's XL, there's XC, so when these two are equal, this has a positive J operator in front of it, this has a minus, which means they're out of phase by 180 degrees. So they're equal, you can think of them as equal magnitudes. So I'll reach an XL value of whatever this is, and I reach the same XC value, whatever it is. Those two numbers are equal in magnitude but opposite. The phases are opposite, so they cancel out. At that point, if I have a circuit, and these two have equal and opposite ohmic values, they cancel out, then the only opposition I have in the circuit is the resistance. And since I've taken opposition out of the circuit, you know from Ohm's law that if originally my current was defined by the voltage divided by the resistive opposition plus the reactive opposition from the inductor and the capacitor, if I'm at resonance and these two right here cancel out, and effectively what I've done is I've decreased my resistance, my opposition, I decreased the denominator here. So if I decrease the denominator, then the current is going to go up. So what happens is that resonance, we get maximum current in the circuit. And so we ended up last class drawing this curve, which turns out to be extremely important. So I want to put that back on the board. This is called the resonant curve. It's a series resonance curve. The way we draw the graph, normally when you draw a graph, you draw it like this. You know, zeros right here. But this graph, we do it a little bit differently. We draw it like this. And zero is still over here, but we're interested in the number out here, away from zero. So on this axis, we have frequency. And up here we can have voltage, we can have current. There's this thing called gain. You don't have to worry about that right now. But we can have, we'll just say V or I up there for now. Now we'll do current. So we'll put current up there. And I asked the question, we know how the reactance behaves. As we get closer and closer to resonance, if this is frequency and this is reactance, we know if I set my frequency in the circuit to 0, at 0, we know that XL or XC is like way up there by infinity, and XL is down here at 0. If you weren't here for that, make sure you review the lecture previous to this one. We talked about the fact that at F equals 0, 0 hertz, basically the inductor is like a short circuit. It's down here at 0, and the capacitor is like an open circuit. It's up there at infinity. And as I turn the knob and I start to increase the frequency, what happens is because XL is omega L, the frequency's in here, and I increase that frequency, then this is going to go up. While XC, since it's equal to 1 over omega C, as I increase this frequency, that's going to go down. So this is moving up like that, and XC is moving down like that. And so as they move along the axis that they're assigned to, at some point right here, this is moving down that way, that's moving up that way. This is the point where XC equals XL, and the frequency at which that happens, we call that the resonant frequency. We subscript that with an R. And so what we did in the last class, we said, okay, well, if that's true, if the resonant frequency is a frequency where the reactive oppositions equal each other, then we should be able to derive an equation for it. And I think that's how we ended the class. We started with this statement right here, XC equals XL. We know the formula for XC. We know the formula for XL. We went through and we solved that for the resonant frequency. And we ended up with a formula that says the resonant frequency is 1 over 2 pi the square root of LC. So we ended up with that. So that's the first formula. So given a circuit, if I give you the value of L and I give you the value of C, then you should be able to calculate for me this frequency right here, FR, the resonant frequency, using this equation. So that would be easy to do. If I give you formula, you got the value for R, you got a value for L, you got a value for C. You put it over here in this equation, you get a number for the resonant frequency, and now you can put the actual value right here. And then the next thing I would have you calculate, I would say, okay, well, since the resonant frequency is the frequency at which XL and XC are equal, you know we're going to have maximum current at that frequency. Let's make a graph of what that current looks like. And I won't go through the details of it right now. We already did that in the other video. You can go back and watch that. But the curve ended up looking like kind of like this, like a bell curve. So it went up and went over like that. And so then we start talking about some points. Like one point you can get right away. You know that at resonance, these two components basically drop out of the circuit. If I measure from here to here, my net reactance will be 0 because these two are equal, but one has a positive phase, one has the opposite phase that's negative, so they cancel out. So the only opposition from the point of view of the voltage source, the only opposition in the circuit is resistance. So what you found then is a maximum current. And so that's this part right here. We said that I max is what you get at resonance when you only have the resistance in the circuit. You can take my voltage source and divide by resistance, and you get the maximum current. Okay, so we got the maximum current right there. We can use this to get that point right there. And then we said, all right, well, if we take 0.707 of that point, then we end up with a point down here somewhere. Now, why 0.707? Well, Jacob, I think it was Jacob, asked a good question. I think you guys had signed off, and we kind of hung around for a minute. And you take 0.707 of this value and you get a point down here. Now, so if that was like 10 amps, then 0.707 times 10, that point right there would be 7.07 amps. Or if that instead was 1 amp, then 0.707 of that would be 0.707. The point is, if I know this value, which I can get because I know R and I know V, I just take V divided by R, I get I max, I take that value, multiply by 0.707, it gives me a point down here. And so Jacob asked the question, well, that 0.707, that's how we calculate the RMS value, and that 0.707 keeps popping up. What's the deal with that? And what I told Jason or Jacob, I mean Jacob, I'm sorry, that I don't know the answer to that, and I haven't looked it up. So you guys might want to look at that. Why does that 0.707 come up? I know it's the RMS value, but I'm not sure here that that's what that represents. So you guys can look that up. I might be wrong. I wondered that myself, but I haven't had time to dig into that like I might want to. I was too busy getting 2 other college degrees, I guess, to think about that. But anyway, the important thing is that when we do this, we got the current here, and we can get the current down here by taking 0.707 times I max. And then if you look at our calculations, what we did, we asked another question. We said, okay, I can get the current, but what about power? What about power? Can I get the power where that curve peaks? Can I get the maximum power? And the answer is yeah. If I got maximum current and I know the resistance, of course I can get power, because I know that power is I squared times R. And if I use maximum current to get the power, then I got the maximum power. That's what this equation will give me. So the other thing I know is that right there where the current is maximum, I also have P max. And then we said, okay, well, I wonder then what would the power be right here? If that's P max, what would the power be right here? And so we went through and we did this calculation, and what we ended up with, again, you can go back and look at the video, I won't redo it here, but what we ended up with was that the power at this point is exactly 1/2 of P max. So guess what they call that point? They call it the half power point. Half power point. And so the power there, I just call that P, capital HP, and that does not stand for Hewlett-Packard. It stands for half power point. And so what that means is, at that point, let's say that P max is 100 watts. With the half power point, it's going to be 50 watts. It's going to be exactly half of P max. So we learned about that. Now, I'm not sure after that what we talked about, but I know what we did. Here's what we did. We said, all right, well, here's something else you can do. We want to suck all the information out of this graph that we can get and see how we can use it to make something happen in the real world. So what we said was, if we draw a horizontal line through the half power point like this, and we intersect the curve by drawing the line right through that half power point, I get a point right here and a point right here, and then I drop a perpendicular down here and a perpendicular down here. And these frequencies here turn out to be pretty important. Those are called corner frequencies or break frequencies. They got a lot of different names depending on whose book you pick up. I just call this F1 and I call this F2. Now the reason F1 and F2 is important is because they define, well, let me draw it for you. Look at this right here. Let me use, I don't know if this blue is going to show up or not. But they define a band of frequencies. Look at this. I can shade this in. And they define something that's really, really important in communication electronics. And I know what you're thinking. Well, hold on a second. This is not communication electronics. This is AC circuits. Well, guess what? I shouldn't say most, a lot of communication electronics is just AC circuits without the wire. What you don't know is, it turns out that if I have a wire, just a piece of wire, and I run a current back and forth, AC, through it, yes, I get current running through the wire, but I also get, basically I create radio waves, electromagnetic radiation. So a lot of what we're learning that happens inside of a wire, you can extrapolate from that, and you can talk about radio waves, and a lot of the same things apply. And so you'll see me kind of move out of the wire, and we'll talk about some of the applications of this here in just a second. So this blue band in here is important because I have a frequency here, F1, I have a higher frequency here, F2, and then I have that center frequency, FR. And that defines not one frequency. See, the thing about it is when we're in lab and you guys are using formulas, you know how to calculate frequency. So say I give you the period of a wave. I'll give you the period. You can take that period and you can calculate the frequency. So you know your equations. You'll say F equals 1 over the period, and you'll give me the period in hertz. It's silly to think about one frequency though. In lab or in an academic situation, you're so used to doing the calculation, getting the number, without really thinking about the practical applications of what you calculated. If I have a frequency of 1 kilohertz, what you going to do with it? All the 1 kilohertz tone can do, 1 kilohertz frequency can do, is maybe give you a pure tone that you can hear, or maybe produce a radio wave. But you can't do much with just a single frequency. And so although we calculate frequencies and we can use frequencies to give us other information in the circuit, like the value of XC or XL, hardly ever in the real world will you deal with one frequency. We always deal with a range of frequencies, and that range of frequencies is called bandwidth. And so let me put that on the board, bandwidth. And depending on what we're talking about, that bandwidth is important. So what is bandwidth? Well, we can calculate it here. Bandwidth is the width. Here's the band. Now, how wide is it? Well, if I know the distance from 0 to F2, and I know the distance from 0 to F1, then the bandwidth is just going to be F2 minus F1. F2 minus F1 gives me this piece right here, which is the bandwidth. And so the bandwidth represents a whole range of frequencies. You've heard of it before, you just didn't know what you were talking about. You probably went over to a friend's house, or maybe you went somewhere and you got on the computer and it was running slow. Other people in the other room, everybody's using the computer at one time, and somebody will say, well, I don't think we have enough bandwidth. You don't even know, what are they talking about? Explain it to me. What is bandwidth? They don't know, they just heard it before. Well, now we know what it is. It's an actual range of frequencies. Imagine this. Imagine you're at a grocery store and you're looking down. You're like God. You have a bird's eye view. You're looking down from the roof through the floor. And you know the grocery store has aisles. There's an aisle right here and an aisle right here, right? It has these aisles. And people walk up and down pushing their grocery carts. Well, imagine that the grocery carts are information that you want to move from point A to point B. And so if I have grocery carts right here, so I have a grocery cart here and a grocery cart here, they can move through this, basically that width right there. But the wider the width, if I have these aisles way wider like this, then I can get a whole bunch of grocery carts in there moving through here, which represents information. Now that's kind of an abstraction, but it's exactly the same right here. When you talk about bandwidth, how much room do you have? How much I'm doing air quotes, how much frequency room do you have to move information back and forth? The more bandwidth you have, the more information you can move back and forth. I don't know if it was with you guys, but I was on, I think at the beginning of this semester, every time I get on this Collaborate thing, I use it all last spring. No issues with it. And this summer I got on there, and every time I would get on at a certain time, the same time, the thing would start crashing. It's like clockwork. When a certain time, it would start crashing. I couldn't figure it out. And then I have you guys, I'm pointing upstairs because I'm in the basement here, but right above me is an apartment. My nephew stays there. And I drill a hole through the floor because I have a router up there, and I have the internet plugged through with a hard wire to the computer over here. And it turns out that he has when I used it last semester, he was at work. So I had all that bandwidth. But when I used it this semester, the particular time I'm talking about were his off days. And I don't know why, it was probably in the middle of the night, it hit me what was going on. He was upstairs playing his PlayStation. He has a PlayStation. And he was playing, well, you guys know more about it than me. You can play through the internet. That takes a hell of a lot of bandwidth. If you're controlling something through that takes a lot of bandwidth. So he was sucking up some of this Collaborate thing takes a lot of bandwidth. And right now, if you guys open your microphones and everything to the camera, you will probably crash the system because of the bandwidth. The bandwidth is so limited from my house to my house. And so he was up there playing the game, and right around the time I was down here do a video, and it would cause the system to crash. But yet when I make the videos at the school, if you look at those old videos I have up on YouTube, the camera quality is better, the lighting is better because I'm at the school, but the bandwidth, the video is almost like a Hollywood production because the bandwidth is so much wider than what I have here in my basement. So bandwidth is huge. Bandwidth is important. Bandwidth is, we can talk about current or voltages traveling through, well, voltage doesn't travel. We can talk about currents through a wire. Wires actually have bandwidth. Everything has a bandwidth. My voice has a bandwidth. Everything has a bandwidth. And so electrically speaking, bandwidth is the amount of electrical room. How much room do I have to send information? The wider the bandwidth, the more information I can get through. So if I have a limited amount of bandwidth on my internet connection, you can only do a couple things at one time, something's going to suffer. If you have a lot of bandwidth, then you can do a whole bunch of things at one time, not even know that I was online or whatever it is you're doing. So this is a really, really important idea. A lot of this transfers not only to AC, but to other courses that if you go for an advanced degree, especially in communication electronics, you'll talk about this stuff. So I want to hit this hard and go through and make sure you understand it. So bandwidth is important. Now let's talk about a little bit about communication electronics, because this will help you to understand this idea of resonance a little bit more. So you guys remember when, damn, I wish I had put this other document up. Now you probably don't remember this, but back in DC I gave you a document. This talked about capacitors. And I gave you a document that had what a capacitor had on the inside of it. There was like 2 or 3 pictures of it. And on one picture at the top, it showed a physical capacitor, and on the inside, they showed I think it was like wax paper. You know, remember, a capacitor it's like an insulator sandwich. It's 2 conductors separated by an insulator, if you remember that. And that document, if you have your 3-ring binder right there, if you actually got a binder and punched it like I asked you to, then what I'm talking about is in your binder. You can probably just flip right through it like that. You'll find a picture of a capacitor that shows what the inside looks like. But at the bottom of that page was well, let me just talk about this. So remember we said a capacitor is 2 conductors separated by an insulator. So what you do is you take a metal plate, another metal plate, and in between you have an insulator. So I'm going to make the insulator red. So that's my insulator. And I make like an insulator sandwich. I put a lead here, I put a lead here, and I can connect those to those 2 leads, and that's my capacitor. I mean, the symbol, it makes you kind of think of that. So here's a lead, there's a plate, there's a plate. That one's bent because when it's polarized, that's the negative plate. So the formula for this, if you remember from DC, that C, capacitance, equals K A over D, where that A is the area of the plate. Right here, that's A. D is the distance between the plates. And K is that dielectric constant. I'm not even going to talk about K. Look at the relationship between C, capacitance, and A. C is directly related to A. If I make the area bigger, the capacitance goes up. If I make the area smaller, the capacitance goes down. Now, let's say I'm going to use this formula to calculate the capacitance of this capacitor right here. What you would do is you'd have to measure the distance between the plates, and you put that number right here. And then you take the area, not the area of one plate, not the area of two plates, the area of one plate. So you take the area of one plate and put that in here, and you look up the constant, dielectric constant in the book, and then you can calculate the capacitance from this formula. But my question is, let me find a prop. I need a prop to show you what I want to show you. So I'm looking around my basement now, looking for something that I can use as a prop. Let's see here. All right. So I got these two books. These are dusty. This is what I use. I teach PLCs up at UC in the summer and the spring. This is the book we use for that, so I have it in my basement. And they got covered with dust. But anyway, suppose these were metal plates. This plate and this plate, this book and this book, they're plates, right? And I got the leads connected to it. So I have a capacitance. So all I got to do to use this formula is measure the distance between the plates, measure the area of the plates, and then figure out, like my dielectric here is air. So I think air has a dielectric constant of 1. So I just put a 1 in for that. So if I measure this area and the distance, I can get the capacitance of this capacitor I'm holding in my hand. But the question I was going to ask is, what if the two plates are not directly over each other like that? What if I have it like that? What if I have one like that? In other words, what if I had one plate like this? What if I have one plate like this? And I have the other plate like this. So they're not completely over each other. I got one like that and one like that. What area would I use? What area would I put in the formula here to calculate? And if you're sitting there thinking, you probably know the answer. You probably use the common area and you will be right. In other words, what you do is, see that little triangle right here, this one? You will use this area. So that looks like a triangle. You know how the formula for a triangle, where 1/2 the base times the height. You can use some geometry and you can figure it out. You can take the area of that triangle here and calculate the capacitance of that capacitor without the plates being directly over each other, right? Okay, well, what if I do this? What if I do this? What if I have one plate like this and the other plate like that? Now the mutual area would be what? 0. If this is 0, then that's 0. If I have no area, no common area, then I have no capacitance. So if I have the plate like this, I have no capacitance. If I have it like that, I have a lot of capacitance. I've not used the whole area. So imagine now I have a fixed piece of metal, and I have another one on a hinge that I can move back and forth like this. I can have it over here, and I can turn the knob, and I have more and more mutual area until I'm like that, I have the whole area, if you follow what I'm doing. That's a variable capacitor. I just designed for you in front of your eyes a variable capacitor. And so I can actually draw a resistor like that. And you know that's a variable resistor. I can take a capacitor and put an arrow through it. All that is a variable capacitor. You probably didn't even know that existed, did you? A variable capacitor. Why is he talking about that? Well, I'm going to show you. Check this out. Go back to our formula for resonance. Remember, resonance can be calculated like this. Right? And the curve for that is like this. Now remember, 0 hertz is on the left. So this right here is 0 hertz. And this is, it goes up from there as I go this way. And at some point, we got the resonant frequency. And given the resonant frequency and the circuit, I can get I max. And given I max, I can take 0.707 of that and get this point. And then on this graph, I can draw a line and get F1 and F2 right away. Just given a few pieces of information, you can get all that other information. But what if I have this? What if I have a variable capacitor? I have a knob I can turn, and I'm varying not the resistance, I'm varying the capacitance. I'm varying C. You see what's going to happen? As I turn the knob and vary C, what's going to happen is this resonant curve is going to move either up this way or it's going to move over that way. By changing the C, you not only move the resonant frequency, you move the bandwidth to the left and to the right. That's pretty amazing. Now, well, I'm struggling here because you guys, I listen to FM radio and AM radio, and what I was going to ask is, do you even know what that is? I know you Similac babies, you do everything. I should call you internet babies or Facebook babies, because you don't even know what Similac is. You Facebook, you do everything through the computer. My nephew listens to the radio, to the music through the computer. Everything's done through his phone. So does anyone out there know what AM stands for? Have you seen the term AM and FM? Let's talk about that. Has anybody seen the term AM? What is this?
AM is the amplitude one, and FM was the frequency one. I forget what the M stands for. Manipulation or something.
Okay, great. Be careful. I got in trouble because I made a comment in class and somebody reported me to this. I'll get excited and I want to say, like, but I got to watch it because I get people take things the wrong way. Not you. I know you guys are better than that, but I get excited that he came up with the answer. That's exactly right. This stands for amplitude modulation. This stands for frequency modulation. Where you would have seen this is if you have a radio in your house, and not your cell phone, but a radio, there's usually a switch on it that says AM, FM. And you can switch it to the AM band or the FM band of frequencies. And you might have noticed, and I don't know if you grew up actually done this, but I grew up with radio. This is pre-internet, so we had to listen to the radio. And you notice that FM, when you you can turn the knob the switch to FM, and it's crystal clear. You turn the AM, and it's staticky. Static, I don't know if that's a word. Static. You know what static is? I'm trying to say static. I just made up a word. Anyway, it's more noisy. It's not crisp. It's not sharp like FM. And I always wonder why. Why is that? Matter of fact, if it's raining and there's thunderstorms outside, you can if you have an AM radio, you never have to look out the window. You can always tell when it's raining, because if lightning strikes, you can actually hear it. You'll hear the strike through the speaker of a radio if it's set to AM pretty much every time. And so that's where you would have seen this. Now, what does it mean? The A stands for amplitude and the F stands for frequency. The M stands for modulate. Modulate. And when you modulate a signal, that means you vary it in a way so that you're putting information on the signal. You vary it in such a way that you're putting information on the signal. Let me show you an example of what I'm saying. Now, what I'm teaching you now is communication electronics, but it's the AC part of it. And I'm doing this because I want to show you that this has applications. And it's not, if you were taking, we used to have a communication course at Cincinnati State. They have two at UC. And you guys are allowed to take it through the consortium of colleges. If they have a course that you want to take, you can take it and pay Cincinnati State prices. We'll talk about that another time. But I would highly recommend taking a communication course if you can, because that's the only thing that we don't have that I wish we did have at Cincinnati State. And I tried to get Dr. Whaley to, we can do these special topic courses as instructors. And I told him, I would really like to do a communications course, because what that course does, if you had AC and DC and digital, it ties all three of those together. And you'll be very pleased with that course if we ever have one. But anyway, so without going into too much theory, I don't know how you imagine radio waves, but a radio wave looks like a sound wave. So let me show you an unmodulated radio wave. An unmodulated radio wave. I guess I can redraw this. I'm going to show you an unmodulated radio wave. So unmodulated radio wave looks like this. It just keeps going. So let's say you go down to the local radio station, you go into where they play the music, the DJ booth, whatever it is, and you hit him in his head, you knock him out, the mic's still on, the transmitter's still transmitting, but you ain't saying nothing. If you were to put that on an oscilloscope, we haven't even talked about it. An oscilloscope lets you see an AC waveform. If you have the microphone sitting there and you're not saying anything, but you can see the radio wave, if there was a way to see it, this is what you would see. It's unmodulated. To modulate it means whatever information that you put, let's say I want to put voice information on the radio wave. There's something about the wave that I'm going to change in direct proportion to the information I'm going to put on it. If I change the height of the amplitude of the signal in direct proportion to the information, it's called amplitude modulation. If I change the frequency in direct proportion to the information I put on it, it's called frequency modulation. And there's actually a third one. PM stands for phase modulation. I can actually change the phase of the waveform, and I can, in direct proportion to the information I'm putting on it, and I can modulate the signal that way. So to modulate the signal means to take a regular, this is called the carrier wave, to take the carrier wave and make it vary either the frequency, the magnitude, or the phase. I vary it in such a way that is in direct proportion to the information I'm putting on it. So what do I mean when I say that? Well, what I'm saying is, say I'm not talking. Here's what the waveform looks like. So here we go. So I got this carrier wave. I'm not saying anything in the microphone. But then I yell, and then I whisper. Then I yell, and then I whisper like that. So I vary the amplitude of the signal in direct proportion to my voice. I yelled, and then I whisper. And if you look, watch this. You see that? And that. Well, in radio electronics, communication electronics, this is called an envelope. So this varying is in direct proportion to my voice, but what you've done is at the top of the carrier and the bottom of the carrier, you created two other sound waves. And those sound waves is the audio that I just put on the frequency. I modulated the signal, so what I can do is I can take the carrier out, and I'm left with this. I take the carrier out, I'm left with that low frequency signal, which is the audio from my voice. And I got that by varying the amplitude of the wave. That's amplitude modulation. Well, maybe instead of varying the amplitude, maybe I do this. Maybe I'm not saying anything, so it looks like this. Then I yell, and then I whisper. I yell, and then I whisper. Now, that's not a very good drawing, but for that part, the amplitude should have stayed constant, but the frequency should have changed. So you should have seen part of it like this, and part of it spread out. Part of it like this, part of it spread out. And again, the part that's closer together could represent a sine wave like that. Frequency modulation. And so the AM and FM just refers to different ways the information is put onto the carrier signal, either by changing the amplitude in direct proportion or the frequency in direct proportion to the information you're trying to transmit. Well, you probably never noticed this because, again, I know you guys don't even listen to the radio. I know you probably just listen to your cell phone. But here's something you probably didn't know. If you ever get a chance to look at a radio, look closely at it, and one of the things you'll notice is that on FM, the frequencies are like so many megahertz. And on AM, all the frequencies are like kilohertz. So right off top, FM has higher frequency than AM. Now, the way it came about, if you look at the history of communication electronics, they discovered AM before FM. So AM was the first way we used to transmit wireless was AM. And then they figured out FM later on. And after that, they figured out TV. So it came AM. I think they had AM back in the late 1800s. FM probably came, I don't know, 20s or 30s. And then TV, like the late 30s, maybe early 40s, it was TV. And so TV actually uses AM and FM when they transmit a TV signal. I don't want to go off on too much of a tangent. Is Dominic out there? I might be able to do it if he's not out there. Oh, he's there. He always wants to talk about me when I go on a tangent. So I can't go on a tangent because the tangent police, Dominic, is out there. So I won't. No more of a tangent than I'm going over now. So on AM, look at this. On AM, I don't know if you ever heard of the FCC. FCC. Anybody ever heard of the FCC? Anybody know what that stands for? FCC? Don't Google it. I know you're probably
Like Federal Communications something, right?
Yep. So you
Commission.
try to Google it. Yeah.
Commission.
You try to Google it, act like you're smart. Federal Communication Commission. Hold on a second. I bet you guys think that's water, don't you?
Straight vodka.
I'm glad somebody's laughing at my jokes. I feel when we're like this, I don't know if you guys are. I don't want to waste a good joke. They're too hard to come up with. Anyway, the FCC is think of them as the communication police, and they really are that. If you were to just go out and randomly, when you get your degree, randomly build a radio transmitter. Let's say you build a 1,000-watt radio transmitter and you start transmitting, they can arrest you. So they set the rules for all communications in the United States. Well, the FCC set it up so that AM stations are so many kilohertz apart. And why would they want to be so many kilohertz apart? Well, the reason is if the stations are so close, they don't transmit at one frequency. It takes a whole band of frequency. Now, you probably wonder why. Well, let me tell you why. Your ears have a resonant frequency. Your ears, your ability to hear, there's a certain bandwidth. You probably don't. Remember I said everything has a bandwidth, and I meant that. Your ears have a bandwidth. The lowest frequency your ears can hear, well, your ears don't hear, the lowest frequency you can hear through your ears is this. 20 vibrations per second. So what sound is some kind of signal that's vibrating your eardrums. And what I'm telling you is the biology teaches us that you cannot hear any signal that vibrates your eardrums lower than that. You can feel it, but you can't hear it. Back a long time ago, this is like when I was in my early 20s, me and my buddy used to install car alarms and stereos in cars. This was around the time we could actually do that. Now you got to have a PhD in electrical engineering to install a stereo. But back in the day, it was simple. And they had a speaker. You guys, we'll talk about speakers at some point in here when we talk about filters. But there's basically, when you have a range of frequencies, you divide it up into three. You got your lows, your mids, and your highs. And this was around the time where hip-hop music was real big and people were riding around with these big bass speakers in their trunk. They wanted that real deep bass. And some company actually made a speaker that wasn't a speaker, it was a motor. What you would do is you hook this up to your subwoofer. If you guys know what a sub, you hook it up to your subs, but the motor would sit under the seat of the car. And when you hit a really high bass note, the bass speakers would kick in, but then this motor would vibrate your seat less than 20 hertz. Now remember, your ears can't respond to a signal less than 20 hertz. So you can't hear lower than 20, but you can feel it. So the idea of that speaker was a motor, was to give you kind of a rattle, give you a deeper bass feel. You can feel bass. If you ever hear a guy go down the street and you're around real close to a really deep bass, you can feel it. And so by having the seat vibrate at a little less than 20 hertz, it made the bass seem a little deeper. So I don't know if it worked or not, because I wasn't into all that loud music. But the point I'm making is the lowest frequency you can hear, humans can hear, is 20 hertz. Anything lower than that, like an earthquake, but earthquakes might be around 7 hertz to 10 hertz or something like that, you'll feel it. you can't hear it, you can feel anything less than that. What about the other end? The highest you can hear is 21,000 cycles per second. 21,000 cycles per second. So now understand what I'm saying. I'm not saying there's not sound higher than that. There is. There's frequencies out there higher than that. I am saying you can't hear those frequencies. They make this thing called a dog whistle. I don't know if you ever heard of it, but the first time I played with a dog whistle, I picked it up and I blew it. You know, a whistle's supposed to go and make a whistle noise. I blew through the dog whistle and it just sounded like air through a tube. I didn't hear anything. But if you do that around a dog or a kid, come running. Why? Because their frequency, God made it so that they hear out here. Their bandwidth is way higher than ours. So bats and rats and mice, they can hear outside of the 21,000 cycles per second. Another story, I had a cat. This cat was the kid. I had foster kids at one time, and I had a cat. It was a stray cat that we kind of took into the house, and this cat would go in the kitchen and just stare at the wall like this for hours. Just sit there and stare at the wall, the kitchen wall. And I was like, "What in the hell what's wrong with that cat? That cat's retarded. That cat is something wrong with that cat." And then the cat would just look at the wall. And then over the next couple of weeks, a little bitty hole appeared over my sink. Well, this is the sink for the foster. I had two apartments, one for the foster kids and one for me. But this hole got bigger and bigger and bigger and bigger. And then one day, the foster kids, they came, "Hey, Mr. Ron. The cat's name was Lucky. Lucky caught a mouse or a rat. It was a rat. I think not a mouse. I'm not even going to lie. It was a rat. And so what happened is this I guess the mouse was behind the sink some kind of way, and he chewed his way out, and the cat probably could hear the squeaks, which was, I'm sure out here I couldn't hear it, but evolution has tuned their ability to hear with frequencies above those which humans cannot hear. And so there are frequencies that exist. The bandwidth for your ears is from 20 hertz to 21,000, and for your vocal cords, it's from 0 if you're not saying anything, all the way up to 3,000 hertz. So let's say I want to listen to music. I got the drums, I got the bass, I got the horns. I don't know all my instruments. I got instruments. If you're a musician, you're producing sounds in this bandwidth right here. You're producing sounds, right? So basically, I'm not going to start at 20. Compared to 21,000, let's just say 0. So the bandwidth for human hearing is from 0 to 21,000 hertz. Well, the FCC, when they set up the radio stations, remember I said AM came first. So here's what they did. They assigned, when you want to start a radio station, you have to buy a license. Now you can't do it because the licenses are really, really expensive. But let's say you can raise a couple $1 million and you buy a license. That license entitles you to a frequency, assuming that there was one open, because the frequency is already set. What the FCC did was, on AM, they had these frequencies. Now this right here is a frequency. That's this. One of these marks is my resonant frequency. That's FR. So when you tune to a frequency, what you're setting is a resonant frequency. So one frequency on AM is 1230 kilohertz. So let's assume that that's right there. That's 1230 kilohertz. That's FR. Now remember what I said, it doesn't make sense to have one sine wave. You don't have one sine wave. What you've done is you set the center frequency here to 1230 kilohertz. But then you still got the bandwidth. You still got the bandwidth. So if you did the thing with the dots that I showed you and dropped the perpendicular down, you have the bandwidth. Well, the FCC put these stations 10 kilohertz apart. So if I go from 1230 up to 1240, that's another station right here. 10 kilohertz up from that is 1240. That's the next station. And then up from there by 10 kilohertz. So the FCC set the bandwidth between AM stations to be 10 kilohertz. Now, does anybody see a problem with that? I'll pause for a minute and let you ponder it. Does anybody see a problem with making the bandwidth 10 kilohertz? Mm-hmm. 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 I'll give you a hint.
Is it like if you're further than 2 stations away, you wouldn't be able to hear anything? Or like you're not getting
No. What's the bandwidth for human hearing?
20 kilohertz.
21,000. Imagine okay, think about it this way, Dominic. Imagine I got an owl, here's my bandwidth. Remember my grocery cart problem? So here's my aisle. Here's one aisle, and here's another aisle. And that aisle is 10,000 kilohertz wide. And I'm trying to carry a pipe through it. So here's my pipe. That represents the information. That represents this. I'm trying to get something that's 21,000. I'm using kilohertz like they were feet. I'm trying to get something that's 21,000 feet or kilohertz wide through a space that's 10. I'm going to cut half this off. You're throwing half your information away. That's the reason why when you listen to AM, it sounds so crappy. Because in order, they have to cut part of the signal out in order to get the information in that amount of bandwidth. I only have 10 kilohertz of bandwidth. I need 21,000. Well, if you look at your FM stations, which you've probably never done, but hopefully after this lecture you will, what you know is about FM. FM uses megahertz. And the FCC set the bandwidth to be 200 kilohertz. The bandwidth of FM is 200 kilohertz. It's huge. It's no problem to get all the hearing, all the audio. Matter of fact, in FM, they can actually transmit hidden signals to make things happen in your room if they want. Because there's so much room there. It's 200 kilohertz. So you can get all the audio through, all your human hearing, all that, plus other stuff. That's one reason you can listen to the same music on AM and FM. AM will sound crappy, FM is smooth as silk. Now, there's another reason too. The other reason is that AM is susceptible to noise. Noise affects the amplitude of a signal and not the frequency. So like if it's raining outside and you turn the AM on, you'll hear the noise, it sounds more static, and lightning strikes, you'll hear that. You listen to the same song on FM, like it's crystal clear. Because noise affects amplitude and not frequency. So that's another reason. But this bandwidth here is the biggest reason. I have so much electrical space to send signals through. But the other thing I was showing you guys is this. In this circuit, if I make this variable, then what I'm doing is I'm taking the capacitor. Where's my prop? Oh. If I make the capacitor variable, I can change the capacitance by changing the common area. Then what I do to my resonant curve is as I turn the capacitor, this curve moves up and down. Now remember, I have a bandwidth here, so I'm not moving. It's improper to think I'm just moving F sub R. I'm not just moving the resonant frequency. I'm moving this whole band of frequencies. So, I got my bandwidth here. And I can move that whole band. That when you tune the radio, when you go from one station to another, what you're doing is you're changing the resonant frequency. By changing the capacitance, you're moving that whole band up and down. You can move it up. If this is your resonant frequency, you pick it up. That center frequency FR, and then 5 kilohertz this, 5 kilohertz that way if it's AM. If it's FM, it's 100 kilohertz to the left and 100 kilohertz to the right. The bandwidth is much wider. And so you get all that frequency for human hearing through that bandwidth. There was something else I wanted to say about this. So tuning, and even when you change now this is a little, but even when you go from one cable channel to another, you're still doing the same thing. In that either fiber optic cable or a copper, they have frequencies, and that even though it's not a radio wave, that those currents and signals are traveling through a wire, that wire still has a bandwidth. Everything has a bandwidth. So even when you change with a remote, you're still going from one frequency to another. I don't know. Hopefully you guys kind of followed that. I know it's a little bit more high level, not high level, but it will come in a course that we will teach after we taught DC and AC. You could take this course in digital, but hopefully I said it in a way that would make you think, hey, this stuff really does have some applications. Anybody have any questions over what I talked about? There was one more thing I wanted to say, but I can't remember what it was. Oh, so TV, I mentioned that. So TV, let me tell you the way that works real fast. Since Dominic's let me get away with it, I can talk about it real quick. So TV actually uses AM and FM. Now, when I say TV, I'm not talking about cable, I'm talking about broadcast TV. So if you don't have cable and you're just getting wireless TV through the air, then what I'm going to say is true. Well, AM, the picture is transmitted in AM, and then the sound is transmitted in FM. So there's actually there's three signals. There's a signal in AM that pictures AM, the sounds FM, and there's another signal called the sync. I can't remember if that's AM or FM or how that's transmitted, but the reason you need that signal is since you're transmitting information, you're transmitting your picture, one frequency, one method, then you're sending out your sound, another frequency, another method. And so you got to make sure that when the guy's talking, the sound comes out when he's moving his lips. So you got to sync the two signals. So that third signal in broadcast TV is a sync signal to make sure that these two things occur at the right time. So that's what that is. So this stuff is kind of dead in the water now because you got cable, you got all these other people watch. Probably most people don't consume TV through wireless now. They either go through their phone or to computer some kind of way. So you don't hear this talked about a whole lot, but a lot of this stuff still applies even if you're using cable or your phone or that. I mean, if you have internet, they talk about bandwidth all the time. I don't think when people talk about internet bandwidth, I really don't think they know what they're talking about. But you as an electrical engineer or technologist or whatever, you got to be very precise about the meaning of things. And bandwidth is just the amount of electrical room. Here's something else. Let me give you another equation. A problem I want to do. I can't remember if I was trying to see. Hold on, let me check something. Do I have this equation written down? I got it backwards. I was trying to peep over there without you guys seeing me. This is not one I use all the time. It's actually FR over Q. So, you know what this is? Bandwidth. This is the distance between F1 and F2 on the resonant curve. Practically speaking, this amount of room you have. When I say room, I mean hertz. How much room do you have to send signals? The wider the bandwidth, the more frequencies you can send through at a given time. But what is Q? Well, Q, let me use green. Q stands for quality factor. Quality factor. Now here's where I told you to go to Blackboard earlier and open those documents. Bring those documents up and you'll see one of those graphs. So let me give you a chance to bring that up on your computer. Maybe you already looked at it, so look at it. And what you will see, let me see if I can draw it on the board in case you don't have it. Let me find it. The graph looks like this. You see your resonant curve. And they have one like this. And they have one like this. Well, let me try to do it like this. And they have one something like this. Now, I don't think I'm doing it justice. That's why I want you to look at the graph. So look at the graph. If you have it or you got it on your screen, bring it up. And let's talk about the graph. So Q, if you look at the graph, if you have it in front of you, this one has a Q of, I think that says 80. I don't have my glasses. I think it's 80. I think this was like 40, and that was 10. The Q, the quality factor. So what the Q, what it does is it gives you the sharpness of the curve. So notice the higher the Q, the skinnier the bandwidth. So if you took 0.707 of this, you get a skinny bandwidth. And as the Q gets lower, the bandwidth gets wider. So whatever this thing called Q is inversely related to the bandwidth. And that's what they're showing you here. This Q, the higher the Q, the lower the bandwidth for a given resonant frequency. Now, the way you change the Q is determined by the coil. I'll give you that in just a second. But so this Q quality factor, what I want you to remember is it determines how skinny or how sharp. The correct word is selective, how selective the circuit is. The higher the Q, the more narrow the bandwidth, the more selective. We're looking at a smaller chunk of that frequency curve, the more selective the circuit. The wider, the lower the Q, the wider the bandwidth. So it's kind of a trade-off. The higher the Q, you got a lot more peak there, so your Imax is going to be a lot higher, but the bandwidth is a lot smaller. And I get a trade-off. If I want more bandwidth, I got to lower my Q down. The way you calculate Q, quality factor, for a circuit like this, Q is the ratio of reactive power to resistive power. So for this circuit, we always use the coil. When I say reactive, we just use the coil. So over here, I don't know why they use the coil, so don't ask me that. I don't know why, but they always use the coil, not the capacitor. I probably should know why. They probably taught it to me in school, but I probably skipped college the day they taught that, knowing me. Anyway, so it's a ratio for this circuit. I know I, right? I know I max. I know I. So it's a ratio of I squared XL to I squared R. So the reactive power, the resistive power for that circuit. And since I have a series circuit and that I is common to both R and XL, guess what happens to the I squared? They cancel out. And so I'm left with this formula that the Q of the circuit, I can find it by just taking XL over R. That gives me Q. Turns out that Q, you know, it has to do with how selective the circuit is, how wide the bandwidth is. But it's pretty handy, too, to get other things. I'll go back to this equation. See, I have three variables here, and one thing I can do is I can get XL right here, I can get XL and R, and I can get the Q using this formula, and now I'm able to use that Q to solve for either bandwidth or resonant frequency. Couple things I want to point out about this equation. One thing I already pointed out was that bandwidth is inversely related to Q, right? So the higher my Q, the lower the bandwidth, and vice versa. You can see that from the graph that you looked at. You can see that's true. The other thing, though, is the relationship between bandwidth and resonant frequency. So bandwidth is directly related to resonant frequency. The higher my resonant, for given Q, that is, if I hold this steady, for given Q, the higher my resonant frequency, the higher my bandwidth. So that's the reason why a lot of, I don't know if you're familiar with radio frequency type things, like the police have a little radio they carry right here with a little antenna on it. They can just push the button and they can talk and cause other police to come. Your cell phone, a lot of things that are wireless. They operate on megahertz or gigahertz. They want them super high frequencies. Why so high? Why do the frequencies have to be so high? Well, if I have a high frequency, right here, if I have a high frequency, I can have a much wider bandwidth for a given Q. And the more space, more electrical space I have to send those frequencies through, the more information I can move at a given time. You don't have issues like somebody playing a PlayStation and causing the internet to crash if I have more bandwidth. And by the way, I don't know if you guys know this or not, but I don't know how they do it. That's not my expertise, but you're paying for bandwidth when you buy internet. That's what you pay for. And they on purpose slow your bandwidth. They slow you down. They give you less bandwidth. You pay for bandwidth. It's kind of like, now you guys, I don't know if you know, I don't have a cell phone. You probably know that. But you used to pay back in the day for minutes, which I just thought was the silliest thing. Back in the beginning of cell phones, people would go get a minute card, and you would go put so many minutes on your phone. And a minute, if you think about it, it's not a real thing. It's an abstract thing, a minute. What's a minute? So bandwidth is the same kind of thing. You're paying for, really, if you can go down and break into, I shouldn't say that, if you can get in a Warner cable or Spectrum or whatever, you can go in there, turn a knob, and turn your bandwidth up. They're not doing anything special, but they'll charge you for bandwidth. You want more bandwidth, you pay more money. And it really should be against the law, what it should be. Everybody should have high bandwidth. And some of the Asian countries, they're going the 5G thing. 5G and the bandwidth, that's all used. And I'll have you do a research on that too. The 5G, I think that's something I might have you guys look into. So this equation is important. So anybody have any questions over this? Okay, I went off on a lot of tangents here. Hopefully you guys found interest in this. I think this is some cool stuff. I do think it was 320. We probably need to do an actual problem. So there's three practice problems I have here, and I'm not going to do all three today. I think I have this session set to expire at 4. Normally I go to 4:20, but for some reason I did it at 4 today. I think something was going on at 4 o'clock. I can't remember right now. So what I want to do is work a problem. I've been lecturing all day for hours. Let's do a problem, and this will drive some of these points home. So take out a sheet of paper. If you have the topic sheet, take that out or bring it up on your screen. Read the problem statement for the first problem at the bottom of the page. Draw the circuit, and then we'll solve the problem. So I'm going to give you a chance to do that. While you're doing that, I'm going to put my circuit on the board, and then I'll read it. So get your calculator, pen, pencil out. Let's do a resonant problem. So this is a series resonant problem. So the circuit I just erased is how you want to draw it. You got your voltage source, and then you got your circuit. All right, let me read it. You guys keep working in case you don't have a sheet. It says you have a series resonant circuit, has an AC voltage source of 10 volts. The phase angle is 0 degrees. The following values are for R, X, and C. They give you 2 ohms for R. They give you 10 ohms for XL. They give you 10 ohms for XC. These two got to be the same because they tell you you're at resonance. They give you a resonant frequency of 12 kilohertz. They want you to find, no, wait a minute. Where did I get 12 from? Resonant frequency is 5 kilohertz, not 12. I don't know where I got 12 from. So this is 5 kilohertz. And they want you to find all these values: the current, the voltage across all the components, the Q, the bandwidth, and the power at the half power point. So I'm going to be quiet. You look at those equations that I gave you. Look at the notes. See what you can figure out. I'll be quiet, let you work, and then we'll come back and solve it together. And then it'll be time for us to sign off.
There's no unit with Q, right?
No. Okay, guys, let's run through this. You probably got the answers. Hopefully you did. If not, I almost fell asleep. I went upstairs while you guys was doing this and laid on the couch under the air conditioner and almost fell asleep, which would have been funny. Not to you, but to me, it would have been hilarious. Anyway, how do I solve for these values? Well, the key is that you're at resonance. And one of the things you know at resonance is when you want to find the current, you do not use the XL and XC because effectively they're not in the circuit. Individually, they are in the circuit, but like if I measure from this point to this point, the net reactance between those 2 points will be 0. The net reactance between this point and this point will be 10 ohms. The reactance between this point and this point will be 10 ohms. But because the phase is 90 for each of them, that means they're 180 degrees out of phase. So this 10 actually has a minus J in front of it, and this has a plus J in front of it. So if you measure here, you're measuring minus J10. You're measuring here, you're measuring plus J10. If you measure here, you're measuring plus J10 and minus J10 is 0. So individually they're there, but as a unit, they cancel. So then that means that the current I get is going to be my maximum current because I get maximum current if I only have resistance in the circuit. So I max is really what that is right there. And that's just V over R. So I got 10 volts, 2 ohms, I got 5 amps. So that's easy. And then I can find, now if you want to, we can do phases. Just want to do phases? We can do phases. Might make it pop a little bit more for you. Let's do phases. All right, so this would be 10 angle 0, and this would be 5 angle 0. So my current phasor would be 2 angle 0. You don't have to do phasors. I don't think they expected that, but the angles might help you appreciate.
You flip flop some numbers.
That's 2 for R.
10. This is 2 and this is 5. Thank you. All right. So now VR. Let's get VR. Let me see. I guess I'll use purple for that one. So we'll get VR. Again, it's just I max, I should write, times R. So watch this. So this is going to be 2. No, this is 5, right? I don't know why I'm getting this confused. This is 5 angle 0. I'll put my units in there. This is 2 angle 0. Look at this. This is equal to 10 angle 0 volts, which is the source voltage. That'll always be the case at resonance. The voltage across the resistor is the source voltage, and that should make sense because these cancel. But look at this. Watch this. Let's get VC and VL. VC is going to be I phasor times XC, and this will be I phasor times XL. This is 5 angle 0. This is 10 angle minus 90. And down here is 5 angle 0. And this is 10 angle plus 90. So here we get 50 angle minus 90 volts. And here we get 50 angle plus 90 volts. So look at this. This is crazy. Look, I only put across the circuit 10 volts. That whole 10 volts appears across my resistor. I got 10 volts across the resistor. And if I individually took a voltmeter or oscilloscope and measured across just a reactive component, either XC or XL, look at my volt, I get 50 volts. 5 times this over here, I get 50 volts. That's one way to know you're at resonance. What you can do is, if I had this circuit, I can take a meter, I can take a voltmeter on AC and hook it to here. And say I vary, now what I'm varying is the frequency, I'm varying this. As I get closer and closer to resonance, the 5K, and what I'll see is the voltage amplitude will rise, and if I go past resonance, it'll start to shrink. So if we were actually doing this in the lab, say we're at the school, we're doing the lab, you wouldn't see the resonant curve like this. This is the way we think about it, but you wouldn't see that curve on the oscilloscope. What you would see is a sine wave, and the way you would know you're in resonance is the sine wave amplitude will get big. And resonance is the biggest it's going to be. If you go past resonance, it'll start to shrink again. So you got that amplitude across here and here, 5 times the source voltage. So at resonance, my reactive components are highly sensitive. If you're actually using this for, let's say, to pick up radio frequency or whatever, you get the frequency at which you tune to the station, you'd have a very, very high voltage for that particular station, radio station frequency on your resonance circuit. 50 volts. Now I'm going to come back to that 50 because I want to show you something else with that in just a second. Notice also that this phasor, let's do a phasor diagram. So VC phasor, these are phasors. These phasors, look at where this is. It's 50 angle minus 90. So it's like down here. VC hat. And this is 50 angle plus 90, so it's up here. VL hat. So they're going to cancel out. So if you measure between here and here, you got 50 volts. You measure between here and here, you got 50 volts. If you measure between here and here, you got 0 volts. Now let's say we go up by order of magnitude. So instead of 10 volts, we got 100. So you multiply everything by 10. This would be 100 volts, and this would be 500 volts. This would be 500 volts. So if you had to grab this at 500 volts, you don't want to do it right here. If you have to grab the circuit, you'll cross 500 volts. You'll cross 500 volts. But if you touch it from here to here, you'll cross 0 volts. You're safe. So you can see the canceling effect if you draw the phasor diagram. So we got, let's see, we got these 3, 4. Now we got to get the Q. Well, that's real easy to get the Q because all you got to do is use that formula I gave you. Bandwidth equals resonant frequency over Q. We'll need that. And we'll need the fact that Q is XL over R. So let's use this. We know XL is 10 ohms. They gave it to us. So we got 10 ohms. I'm going to write it as 10 because this is in ohms. That's in ohms. They're going to cancel. So we got 10 divided by 2. So my Q is 5. So in this formula right here, I can put 5. Q doesn't have any units. It's a unitless quantity. It's a figure of merit like efficiency. We talk about efficiency. Q is the same thing. So we know Q is 5. We also know my bandwidth is 5 kilohertz. Now, let me go back to Q for a minute. Q is 5. Look at this. If you take, let me do it over here. Actually, right here. If you take Q times V source, you get the voltage across the reactive component. So, like if I take Q is 5, I take 5 times 10, I get 50 volts. And 50 volts is what we got across VC and VL. Now, this is called Q magnification. The fact that the voltage is higher than the voltage source for across my reactive components is called Q magnification. This actually is important if we're actually dealing with radio frequency. You have a circuit, communication circuit. You want whatever frequency you tune to be way higher than the other frequencies. As a matter of fact, when we're done with this, I'm going to go back to the graph and show you one more thing about that. So we got all the voltages. We got my Q. We got bandwidth. Is that right? I got 5 kilohertz and 5. So that's 1 kilohertz. So bandwidth is 1 kilohertz. Now they didn't ask for this, but given a bandwidth of 1 kilohertz, are you guys able to calculate F1 and F2? How would you find F1 and F2? What would you do to get that? They didn't ask for it, but how would you get it? Just by looking at the graph.
Would you take half of it and add to the resonant frequency, and then half of it and subtract from the resonant frequency?
Exactly. And let's see what Jacob's talking about. So we know the resonant frequency is 5 kilohertz. And we also know that the curve looks like this. And we know that if I draw my points, this is the point, my half power point, and I draw my line through, I know this is F1, and then this right here is F2. And what he's saying is the bandwidth is right here. That's the bandwidth from there to there. Well, if I take the whole bandwidth minus half the bandwidth, this half gets us the F1, and the bandwidth plus this half gets us the F2. So if I take half the bandwidth, well, the bandwidth for this over 2 is 0.5 kilohertz, 500 hertz. So if I take a 5 kilohertz and subtract 0.5 kilohertz from it, over on this side, I get 4.5 kilohertz. So that frequency right there is at 4.5 kilohertz. And if I take the bandwidth and add 0.5 to it, then this frequency right here would be 5.5 kilohertz. So that right there is F2, and this will be F1. Now, they asked for the power at the half power point. We're going to end this because I want to end it at 4, but I want to show you, there's one more thing I want to show you about power. We can get to get the power at the half power point, we find the max power in the circuit. Remember, that's just that equation with the resistor. So that's not a big deal at all. Let's go ahead and get that. My P max, the equation for P max was just I max squared times R. For I max, it was 5 amps, so I got 5 amps squared times 2 ohms. 25 times 2 is 50 watts. So at that top point right here, I have 50 watts. Right here, 50 watts. But they want to know the power at this point and this point. Well, that's the half power point, so it's going to be half of 50. At that half power point, the power is 25 watts. Okay, so that's easy to get, easy to calculate. But let me show you this. This is another reason. Let's go back and say we're talking about radio waves again instead of signals on the wire. If we're talking about radio waves, and I set my tuner on my radio to pick up or transmit at 5 kilohertz. As long as I'm in this band of frequencies right here, let's say I'm receiving that signal through a receiver. As long as I'm anywhere in this band, let's say I have someone on another frequency and they're transmitting over here. So whatever this frequency is, that's where they're transmitting. And my station is tuned to this. You see that right here at this point, any signal at this point, 25 watts is what I can pick up or transmit. As I move towards resonance, it moves up to 50 watts. I move over to my other corner frequency, it's back down to 25 watts. Well, this guy's over here. Look at his power. His power is way down from 25 or 50. So it's almost non-existent. If I have a radio station transmitting outside the bandwidth, the power is decreased, or the word is attenuated. Decreased, attenuated. So much that it wouldn't affect anything in the bandwidth because of the steepness of that and how far it is from the half power point. So anything outside the half power point, we just consider it non-existent. Ideally, the bandwidth would look like this. If I had an ideal curve, ideally the bandwidth would look like this. And this would be F1, this would be F2. And so anything over there, and you'll see, well, in this class, one of the things we'll talk about towards the end is filters. And you'll see when we draw the bandwidth for a filter, we draw the ideal filters don't look exactly like this. So we'll revisit all this stuff. So that's a basic resonant calculation, and that's really, I mean, we can go in a lot of depth. This was a communication course. We can go into a lot of depth with this stuff, but for what we're going to do in AC, I just want you to kind of stick your toe into the pond of resonance and just kind of see what it feels like. Now, we do need to do these other problems. We just won't do them today because, like I said, I think I set the session to aspire at 4. But if you want to work ahead, we got 2 more problems on the sheet. If not, during the next session, we'll do the other 2. I'll talk a little bit about parallel resonance, just briefly, and then I want to move on to another topic. Either it's going to be transformers or filters. Normally, I talk about transformers next. I toyed around with the idea of flipping it and talking about filters. I don't know. We'll see. But we'll finish up resonance in the next session, and then we'll move on to a new topic. Now, guys, I may have mentioned this already. I need to bring you into the lab because it's just, Whaley wants to do this remote thing, but there's no way to do AC remotely. I mean, we can't do anything without an oscilloscope. I can give you, and I'm going to give you the other lab as soon as I can get them scanned. I've been saying that, but you got to put your hands on the O-scope. We got 2. We got an analog O-scope, which I know everything about, and we got a digital O-scope, the new school O-scope, which you'll know everything about. It's menu driven. But what I'm saying is we're going to have to coin out some time to go up to the school as a group. Now, there's only a few people in the class, so I'm not too worried about it. But whenever that is, I don't know if it'll be this week or next week, you'll need a mask, and we'll have to see what other rules they're going to have in place. I got to run this by the dean and everything, but we're going to have to do it because you need it for labs, so there's no way they can say no. I just don't know how that's going to look. So we'll have to bring masks, and I think I don't know, we got 4 or 5 people in the class. We can spread out, and we won't be on top of each other. So, but if you're feeling sick or something like that, you won't be able to participate in that. So I'll have more to say about that. I got to contact the technician, the lead tech over there. He'd been in Florida for a couple weeks, and I thought he was still in Florida, but I talked to the executive secretary, and she said, no, he's been back. So he told me he would be out for a couple weeks. So I'll contact him, and you'll hear more about that. Probably plan on next week is what I'm going to shoot for. But I'll let you know. So just keep watching Blackboard. Whenever I can get stuff posted, I will. And before we sign off, 2 things. Number 1, even though I've been forgetting this, do not forget to text me for attendance, just in case you don't have the number. I think you probably do, but I'll put it up here again. And your class is EET 132. Put your name in there. And the other thing was, does anyone have any questions before we sign off? Any questions?
I have a couple, but I don't know if they need to be on the recording or not.
Okay, well, hold on. I'll turn it off in a second. Anybody have any questions I guess I can turn it off now. I don't put these on YouTube. So the other ones last semester, I put everything on YouTube because I just figured with the Blackboard